Hi, everyone. The theoretical framework underlying our modern understanding of particle physics is known as quantum field theory. Why do we need this new framework for describing particle physics, though? Well, in 1905, Einstein taught us about special relativity. Now, special relativity is very important for describing objects which are moving very fast. Now, that's not to say it doesn't also accurately describe things that are moving slowly. It just reduces to classical physics in the slow limit. And so we really only need it when describing fast moving objects. So special relativity tells us that things behave in unusual ways when they're moving very quickly. And when I say fast, I mean some significant fraction of the speed of light. And we learned there that strange things happen, such as time dilation and length contraction. Now, one of the fundamental aspects of special relativity, which is really different than the way we thought about physics before special relativity, is the fact that it treats space and time on approximately equal footing. We really stop thinking about space and moving through space as some function of time. And instead, we think about moving through this thing known as space-time, where time is really just thought of as sort of like another spatial dimension. We treat it a little differently, but we put them on pretty much equal footing. And that's one of the fundamental aspects of special relativity. Quantum mechanics, we've known about since the early 1900s, and it describes objects that are very small. Again, it also works for larger objects. However, it's also sort of unnecessary to use quantum mechanics when describing large objects because classical physics works approximately well when objects are large. And by large, I mean sort of everyday human scales. Quantum mechanics becomes very important when we're thinking about very small objects. Now, in quantum mechanics, we have the Schrödinger equation, which explicitly treats space and time differently. The number of derivatives that are spatial versus the number of derivatives which are temporal are different in the Schrödinger equation. So we're seeing that sort of symmetry that we have in special relativity is not present in quantum mechanics because this way in which we're treating space and time differently. And so we have a conflict here where special relativity and quantum mechanics don't actually fit together. And in fact, one might even want to call the quantum mechanics that you first learn about non-relativistic quantum mechanics because it explicitly is not a relativistic theory. Similarly, special relativity doesn't obey the laws of quantum mechanics all on its own. It does not accurately describe objects which are very small. And so while these two theories are very fundamental and work very well in the appropriate limits, they don't actually accurately describe everything. And so physicists needed to reconcile this because we know that these are fundamental aspects of our reality. And in trying to combine special relativity and quantum mechanics, what we end up with is quantum field theory. And so what quantum field theory really is, and here you see it's abbreviated as QFT. That's usually quantum field theory is said just QFT. What quantum field theory is really the marriage of special relativity and quantum mechanics. So this is a more fundamental theory which accurately describes objects which could be very small and moving very fast. Now, this is a very good framework for describing particle physics because, of course, particles are very small. And when we're studying particle collisions, say at the Large Hadron Collider, they're moving very fast. So we need a theory which is both relativistic and obeys the axioms of quantum mechanics. And that's really what quantum field theory is and what it's going to do for us.